So far, we have agreed that how to calculate the potential at any point if we know the distribution of the charge. And actually, we cannot calculate the potential at a point, but we can calculate the potential difference between 2 points. And in order to find the potential at a point, we have to choose another point as a reference to us that has zero potential, and by choice we choose infinity to be that point. So in order to get the potential at a point, we need to choose another point to have a zero potential. And the potential is given by that equation. If we know the electric field, then the potential between 2 points in space equal to negative the integration between from point 1 to point 2 for E dot dl or for dl dot E. The potential energy equal to the charge times the potential. The potential energy, that's a scalar quantity. Potential is also a scalar quantity. It might have a sign, but the sign does not mean direction in here. The conductor in any electric field, they become an equipotential surface. The conductor in any field, they become an equipotential surface. What does equipotential surface mean? They have the same potential everywhere. So if you have a conductor and you put it in a field, that conductor become an equipotential surface. The difference in potential between any 2 points on the conductor is equal to 0. I'll say that again. The difference in potential between any 2 points on the conductor equal to 0, because that's an equipotential surface. The electric field is always normal to a surface of the conductor. The electric field will be always normal to the surface of the conductor, whatever the shape of the conductor is. Those are the two information that we know so far. Then, if we know the electric field, we can simply get the potential. If we know the electric field, then the potential between 2 points equal to the negative the integration of for E dot dl. We know that. The potential, if we know the electric field, we can get the potential. But if we know the potential, can we get the electric field? So can we deduct the electric field from the potential? The answer is yes. It's exactly the opposite of that operation, which is the electric field that's negative, the partial derivative of the potential with respect to that specific coordinate. So if we need to find the electric field along the x-axis, then it's negative the derivative of the potential with respect to x. The electric field along the along the y-axis, that's negative the derivative of v with respect to y. The electric field along the z-axis, that's negative the derivative of v with respect to z. Those three operations, we write them in a more summarized form that says that the electric field equal to negative the gradient of v. The gradient of v, and that simple means that the derivative of v with respect to x, the derivative of v with respect to y, and the derivative of v with respect to z. So that gradient means that. So that simple gradient means the derivative of v with respect to x along x, plus the derivative of v with respect to y along y, plus the derivative of v with respect to z along z, and that's in the Cartesian coordinate system. But if we go to the spherical coordinate system, then delta v, the gradient of v means something else. We're not going to go there. It's on the slide, but we're not going to use it in this course. Attabi, ask. No, we're not. So, saying that and looking at this example in here, if we have the potential as a function of x, given as a function of x, at which point or points is the electric field 0? Where can we find electric field equals to 0? E, back, let's go back. E, that's the derivative of v with respect to x. That's the gradient of v with respect to x. So in here, which one, which one will have zero gradient? Which one will have zero change? Just before it and after it. That's B. If you have a curve, you get zero gradient at the maximum point or at the minimum point. Right? Right? Right, guys? So the change in here, if you have this curve, any function, the change in here is zero, the change in here is zero. There is a change in here in that function as a function of x. That function as a function of x, the gradient here is zero, the change here is zero, the change in here is zero, here is a change, there is a change in here, there is a change in here. So you get zero change only along at the maximum or at the minimum point. That's why you get the answer is B in that case. So there is another example, numerical one, not graphical one. If you have V is given by 3x squared plus 2x minus z squared, then can we find the electric field along the x-axis? Yeah, that's Omar, that's easy. The electric field along the x-axis, that's negative the gradient of V, or negative the derivative of V with respect to x. So the derivative of V with respect to x, I believe you guys, can you find the derivative of that? With respect to x, it's going to be 6x plus 2y. You're doing partial derivative. That means that you're doing derivative with respect to x only, and anything else will be constant. That's why that derivative here, it's a little bit different than d over dx. It's partial v, partial x, which means that everything else does not depend on x. Y and they do not depend on x. So that's it. Minus x minus 2y, and partial e and ey, it's going to be minus the derivative of v with respect to y. And so if you do the derivative of that function with respect to y, you get 0 in here. You get 2x in here, and you get 0 from that. Because there's no y. You're doing derivative of x, of constant, of x, which is constant, with respect to y. Okay? So you get negative 2x. And if you do the derivative, the partial derivative of that function with respect to z, you get 0 in here. Second term will give you 0 as well. The derivative of the second term will give you 0. The derivative of the third term is going to give you minus 2z. And there is another minus in here that you get the answer is 2z. And this is the electric field. So you can write the electric field now as an x component, a y component, and a z component. And that's what you see. Yes. Coordinates. So now if we need to find the electric field at points x equal 2, y equal 4, and z equal 5, then you can find the numerical value for the electric field. Yes, Ala. Excuse me? Why there is a negative? Okay. No. Oh, that negative, that came when we were trying to prove that. If you remember, when we were trying to prove that formula, at the beginning of that chapter, we came up with that negative sign. And it's always carried with us. So if v is negative of the integration of E dot dl, then E is negative the derivative of E, of negative the derivative of E is the negative derivative of V with respect to the coordinate. So that's why we have the negative. And that's, you can go and look back at the, yes. It's in the opposite direction to the Coulomb's force. Yes. So so that part is easy. If we know E, we can easily find V, and if we know V, we can easily find E. Okay. Now, We have an electric potential in the region in space that's given by 2x squared minus x cubed. Guys, can you find which one is the correct answer? A, B, or C? We need to find the x component of the electric field at x equal to. We have the potential given by 3x squared minus x cubed. And we need to find the electric field along the x-axis at x equal to. So how can we find the electric field? Minus the derivative of v with respect to x. Right, Dina? So let's do that derivative. It's minus 6x plus 3x squared. Plug in the numbers, then you get 0 electric field. What do you mean by عليهم كلهم? What whole bracket? I don't see any brackets. Rate of change of electric field is the gradient of V, which is the derivative of V with respect to x. So do the derivative of 3x squared, 6x, and you have a negative sign. Remember that. Do the derivative of x cubed, 3x squared, and you have a negative sign. Then you get, plug in the numbers, which is x equal to 2, you get 0. So the bottom line, so far, that what we know that the potential difference between point A, P, and A equal to the work done divided by the charge, or the potential energy divided by the charge, or you can look at this equation in a different way. You can say that the potential energy equal to Q0 times the potential difference. And a potential difference can also be given by the integration from A to B. The potential difference between B and A is the integration from A to B for E dot dl, or in other words, if we know E, if we know the electric field, we can find the potential difference between any 2 points in space. Yes. No, the potential difference in the potential energy equal to the work done. That's why when I said in that equation, I said the potential difference equal to the work done divided by Q0, or you can say it in other words, the potential difference equal to the potential energy divided by Q0, which means that the potential energy equals to the work done. And if we know the potential, we can find the electric field. So those two equations, they tell us, if you know the electric field, you can get the potential difference between 2 points. If you know the potential as a function of a coordinate system, then you can find the electric field anywhere. Of course, the integration of a derivative is, so get this thing. Units of a potential, that's 1 joule per coulomb. The potential difference or a potential has a unit of joules, that's the units for energy, divided by coulomb, that's joule per coulomb, and then we're going to call joule per coulomb, we're going to call it volts. I'm going to skip that slide. I'm going to skip, if you want to read it, that's fine, but I'm going to skip it. I'm going to go to part 2 of that chapter.